F is an we first of all we recalled certain formulas of integration. Most of them we know already for L is equals to pi. So the first observation is that whenever we have the function f which is odd function, then integral over the symmetric interval minus some number 2, that number is 0. Similarly, if the function is even, then the integral will be 2 times integration 0 to that number. The same way we studied properties of sine and cosine function. So in all of this formula, the important thing is that the interval over which we are integrating is symmetrical. It is from minus L to L, right? Where L is some positive number. So sine integral is 0, cos integral is 0. Here we have proved that the inner product of sine m pi x by L is with cos n pi x by L is 0 for any value of m and n. But in this formula, when we have same function, there are two cases. Either m is equals to n or m is not equals to n, depending on the value of the integration is either 0 or L. Similarly for the cosine function. And then we discuss periodic function. We know the example of periodic function, which is sine and cosine function, which has period 2 pi. So what is L? L is basically the half of the period. So whenever we have, so we know that cosine and sine function are integrable functions and its period is 2L. So whenever we have such a function which satisfies this property, that we have the function which is 2L periodic and it is also integrable, then we can expand that function in terms of cosine and sine function. And in that case, we will write the function in the form of series, right? So corresponding to this function, the series is this right hand side series, which is known as Fourier series, where the Fourier coefficients are a0, an, and bn, right? So this a0, an, bn are known as Fourier coefficients. And yeah, so how do we find that? Depending on what function is given, we substitute the function here and we shall find a0, an, and bn, depending on what L is given, right? So function is given which is 2L periodic. Depending on that L, we find the Fourier series. Yeah, so we will study later on that when this Fourier series will be equal to the value of the function at that particular x, right? So that is a separate thing. But first question is, what is the Fourier series corresponding to given function? So we'll see some examples today regarding that. So first of all, we observe that whenever L is pi, that means we have the 2 pi periodic function. So f is 2 pi periodic function. The Fourier series formula is this one, where Fourier coefficients are given by these formulas. And either the period is 2L or period is 2 pi. Whenever the function will be odd, ans will be 0, right? Because the function is odd function. So Fourier coefficient an will be 0 in that case, and we'll get only bn part of the series. Similarly, whenever the function will be even function, all the bn's will be 0 and we shall get the only cosine terms. So basically other than sine terms. So in general, so here we are saying that for odd function, this series is sine Fourier series, right? For even function, this is cosine Fourier series, right? But this both part will always be there for any function, right? So whenever we expand the function, shall always get cosine part as well as sine part. So whenever we say that cosine series of function fx, that always means this part, and whenever say that sine series of fx, that means we are talking about this part. So every function has two parts, cosine part and sine part, in that way. So this is regarding the terminology. So today we want to discuss the first example, which is we want to find the Fourier series expansion of the function fx equals to. So this is a step function, right? So it takes the value so what will be the graph of this function? Minus pi to 0 and 0 to pi. So whenever value of the function is from minus pi to 0, yeah, so x is between minus pi to 0, the value of the function is minus 1. So this point is not there. Up to 0, it takes minus 1 value, and then from 1 onwards, so this point is not there. At x equals to pi, the value is 1. So this is graph of the function in the interval minus pi to pi, and it is not mentioned, but uh, the function should be periodic whenever we are finding the Fourier series. So let me mention here that the 2 pi periodic function.
Sir,
Yes.
sir, at pi also there should be not equal to
Right.
1.
Yeah. So you are right. So we need to take either minus pi or pi. We need to define the function. So now is it fine?
Yes, sir.
Right. So you are correct. So we need to define the value of the function over the interval starting from the first point of the to the last point. One of the point we can ignore because it is 2 pi periodic function. Yeah. So now what does this means? This is a 2 pi periodic function. That means this function will repeat. So from, let me use the some other color in that case. Yeah. So now again the function will start. It is 2 pi periodic function. So it will start like this. Right. The interval pi to 3 pi, because the function is 2 pi periodic, it will be defined in this way. Similarly on this side. Okay, so this is regarding graph of the function. Now let us find the Fourier series. So what can we say about this function? First thing we'll observe is whether it is odd function or even function. So if we substitute, instead of fx, we substitute f of minus x, then for example, we substitute f of minus pi by 2, then we get the value minus 1, right? And if we take f of pi by 2, we get the value of function to be 1. So the sign is opposite at minus pi by 2 and pi by 2, right? So we can see that the function is an odd function. So here fx is an odd function. So we have observed that whenever we have the so one more thing to note is also the period is 2 pi, right? This is a 2 pi periodic function, therefore we have L is equals to pi. So we shall use the series formula for the uh, whenever L is equals to pi. So this formula we shall use to find the Fourier series, because L is equals to pi. And we already know that whenever f is odd function, all ans will be 0, so we will only get the sine series of that function, right? So since f is an odd function, a0 and each other an will be 0. So to find the Fourier series, we need to only find the bn's. So let us find bn. So now for any natural number bn, we know the formula is minus pi to pi fx sin nx dx, right? So now we need to integrate the function over this interval, and the function is defined into two parts, -1 and 1. And on the other hand, we also know that the function is odd function. So using the property of odd function, we can simplify this integral as a so f is odd. What about sine function? Sin nx is
Or
odd, that is also odd, right? So odd into odd will be even function. So this is even function. So that means we can write the integral as 2 times over the half interval. Because fx into sin nx is an even function. Fine. So now we need to only look at the value of the function fx over 0 to pi interval, and we know that over the 0 to pi interval the value of the function is 1, that is a constant function 1. So let us substitute that. That means we get integral 0 to pi sin nx dx. So now here the interval is not symmetric, that means we cannot use this formula. Right? If interval is symmetric, minus L to L, we can use this formula, but here we can't use that formula. So that means we need to evaluate this integral by integrating it. So integral of sin nx will be minus cosine nx divided by n. The limit is from x equals to 0 to pi, and then we know that this is 2 times 2 divided by pi. So what we get is minus cosine n pi plus cosine 0 divided by n. So we substitute the limit in the integral, and yeah, so what is cosine n pi? Cosine pi is 1, cosine pi is -1, cosine 0 is 1. So in that way it is alternating the sign. So what we get is minus 1 power n, that is the value of cosine n pi, plus cos 0 is 1 divided by n. So basically this depend on whether n is odd or n is even, essentially. Yeah, so we got our bn in terms of n. So let us write down the Fourier series now. So therefore the Fourier series of the given function is fx represented as, so since a0 and an is 0, we will get only bn part, and we have already found what is bn. Let us substitute that. So what shall we get? We get n is equals to 1 to infinity.
So Bn sin nx.
Just a minute. Bn, yes, you are right. So bn has sine part, correct. Yeah, so if you have any doubt or I do any mistake, just unmute and tell me. Right, don't raise the hand because I'm not checking that during the lecture. Okay, so thanks for that correction. So now we will substitute bn value, and bn turns out to be 2 pi divided by 2 divided by pi minus of minus 1 power n plus 1 divided by n times sine nx. So we can expand this term by term also. So if you substitute, this is a constant term, we can take outside. The remaining term is summation, this time sine nx. So for n is equals to 1, this will be minus 1. So minus minus plus 1 plus 1. So we get 2 divided by n is 1 times sine nx, n is 1. So we get sine x, plus we substitute n is equals to 2. So we get minus 1 power 2 is 1. So that will cancel out, right? So the numerator will be 0 for n is equals to 2. So that means sine 2x term will not be there in the series. The next term will be for n is equals to 3. N is equals to 3, we get, again in the numerator we get 2 divided by, the denominator will be 3 because n is 3, right? And sine 3x, plus next term will be 2 divided by 5 sine 5x onwards. So the even sign terms are cancelling because of this numerator formula, depending on whether n is odd or n is even. Fine. So this is the first example. Let us quickly take the second example. So if we have the function phi fx equals to x, and which is periodic function, and the period is arbitrary. So let us say L is some period. 2L is the period where L is positive number, and we need to find this expansion of the function. So since f is an odd function, a0 and an are 0. So again we need to find bn only. So bn general formula is 1 upon L minus L to L fx sin nx by L. So fx here is L sin n pi x by L dx. So we shall use integration by parts, and we know that derivative of x will be 1. So that means we shall differentiate that function. So we shall get, first of all, it is an odd function, so we get 0 to L sine n pi x by L dx, because odd into odd is even. So this is an even function now. So the integral will be 2 times over the half interval, and if we integrate this integrand, then we get minus x cos n pi x by L times the coefficient of x. We need to take the reciprocal of that. So that will be L divided by n pi, and the limit will be from 0 to L. So this is the first term of the integration by parts. The second term will be integral 0 to L cos n pi x by L into the number, this number. So again we need to integrate this. So we will get, so if you substitute the limit here, if x is 0, this term will be 0. If x is L, then what we shall get is this angle for x equals to L, it will be cos n pi. So we know that cos n pi is minus 1 power n, right? Just now we use that, times minus L, because we are substituting x equals to L, times L divided by n pi. So that is this term when we expand it, and the remaining term is minus. When we integrate this function again, L by n pi will comes out, so we get L square divided by n pi square times sine n pi x divided by L, and the limit of this is from x equals to 0 to L, right? So now, yeah, so just check that. Now we need to substitute the limit here. So if we substitute the limit, let us simplify this. L into L, L square, n pi minus 1 power n minus L divided by n pi square. When we substitute this limit, we know that sine 0 is 0, and sine n pi will also be 0. So both the limit will be 0, and essentially we get the last term. L will cancel out, this part is 0. So in the first term, L will cancel out, and we get 2L divided by n pi minus 1 into minus 1 power n. So that will be minus 1 power n plus 1. So for the general periodic function, 2L periodic function, fx equals to x, ens are 0, and bn is this particular value. So we can expand, we got the expansion, n is equals to 1 to infinity 2L divided by n pi minus 1 power n plus 1. So that is bn times sine. Yes. So this is the Fourier series expansion. We cannot find the general sign values because that involve L, right? But now we can take different values of L. L is equals to 1, 2, pi, whatever, and using this formula we can find the corresponding series. Okay, so this is regarding the expansion over general interval. Now the question is that when the value of the function will be value of this series at particular value of x, whether left hand side is equals to right hand side or not. So there is one result regarding this, and that is known as convergence of Fourier series. So what does this means? This means that so far we have only found we are given function f, its series is this one, but we did not discuss when this series will converge, right? So we know that the series is not important. The important thing is whether its sum is a finite number. So that means whether the series is convergent. The first question is whether when this series will be convergent for which values of x, and among those values of x, when this number which is sum of the series equals to f of x for which particular x, right? So if we can find that, then we can write fx is equals to this series. So let us write down the statement. We will not prove this result. So if a periodic function fx with period 2 pi, so we shall state this result only for 2 pi periodic function, but that also is true for any general periodic function. So if the given function is piecewise continuous function, minus pi to pi, right? Yeah, any doubt? Okay, so if the given function is 2 pi periodic function which is piecewise continuous in the interval minus pi to pi, and it has a two-sided derivatives, so that means left derivative and right derivative at each point of the uh, interval. So interval here is minus pi to pi. So in this case, that means at the point where the function is has left and right derivative, the Fourier series converges at that point. So not only the Fourier series converges, it converges to fx. And only problem is this function we are assuming is piecewise continuous. So piecewise continuous means it may have jump discontinuity, right? So whenever it has discontinuity at a particular point, so that means except at the point x naught where the function is discontinuous, we the series converges to the average. So average means basically the left limit at that point plus right limit at that point divided by this. So it converges to this number. So we are what this result says that if f is the periodic function and it is 2 pi periodic continuous function over the interval minus pi to pi, and at point x naught if left and right derivative exist, actually this requirement is for each point, then the Fourier series converges at the point x naught and it converges to f of x naught. But if x naught is at x naught the function is discontinuous, then the Fourier series converges to the average value. Okay, so here the assumption of derivative exists, that is the proof basically is using integration by parts, and therefore we need to differentiate the function f dash, right? So that's why the assumption is required to be differentiability. So you can see this proof in book of Irwin Frizik, Advanced Engineering Mathematics, if you are interested. So let us see the application of this theorem. First, we shall find Fourier series of a function, and then we'll see when for certain points what will be the sum of the series. To find the Fourier series of the periodic function, so the function takes value 0 over the interval minus pi to 0, and value is x square if 0 less than equals to x less than pi. Okay, so this function is given. Now if here less than or equal to given, that is also fine, because anyway it is a 2 pi periodic function, so f of pi will be f of minus pi, right? So don't worry about that. And then find uh, the expansion of pi square by 6 using this series. Yeah, so let us first find the Fourier series of this function. So we start with a0 term. A0 term is 1 upon pi minus pi to pi. So it is not mentioned that this function is 2 pi periodic, but the value is given between minus pi to pi. That means it is a 2 pi periodic function. So when we integrate this, we get the value of the function is 0 on this part. That means we will integrate over 0 to pi only, and over that the value of the function is x square, and that will be 1 upon pi x cubed by 3. Limit is 0 to pi. So this will turns out to be pi square by 3, right? Because 1 upon pi cubed by 3, pi will cancel out. Essentially we get pi square by 3. Similarly, an will be 1 divided by pi minus pi to pi fx cosine nx dx. So again here also the interval over which the value of the function is 0 doesn't matter. So that means we shall integrate over the interval 0 to pi. Now, if you want to integrate this function, we need to use generalized version of the integration by parts, that is known as Leibniz formula. So that says that we need to differentiate the function whose derivative will be 0 after some time. So we know that x square function derivative will be 2x, and again we do differentiation, the derivative will be 2. So we shall keep differentiating the first function, keep integrating the second function. So we shall get x square. The first integral is of course cosine nx is sine nx divided by n. If we differentiate 2x again, we get differentiate x square again, we get 2x times integration of this function, that will be cosine nx divided by n square, right? And yeah, so here why we are getting plus, because in the second term there should be minus, and the integral is will have minus sign, so minus will become plus essentially. In third term we have plus sign, with derivative of 2x function is 2, and again integrating this function will get sine minus sine nx divided by n power 3, right? So sine in this formula is alternating plus minus plus, and now we substitute the limit x equals to 0 to pi. So this is you may have seen this earlier also, this formula. So this, let us substitute the limit now. So if we substitute x equals to 0, then sine terms will be 0, and we know that cosine term cos 0 is 1, right? On the other hand, if we substitute pi, then also sine terms will be 0, so only cosine term will remain in that case, and we know that cosine and pi will be minus 1 power n, right? So yeah, so what shall remain now? Yeah, but in that x equals to 0 case, this term will be 0, so only one term will remain, that will be when this term when x equals to pi, so that is plus 2 pi divided by n square minus 1 power uh, n, right? Yeah, but this minus minus will be actually plus, because outside also there is minus. So we get this term. Now what will cancel out? Pi will cancel out, so we get 2 minus 1 power n divided by n square. So we have found nth term. Now we need to find the, similarly using integration, we need to find what is bn term. So bn term will be by the formula. This is a 2 pi periodic function, so we use the formula, Fourier formula for the 2 pi periodic function. Again, the function is 0 over minus pi to 0, so that means only we will integrate over 0 to pi. So now we shall use this formula again, the Leibniz formula. So this will be 1 divided by pi, the integration will be x square times minus cosine nx by n minus 2x times integration of cosine will be sine nx divided by n, so that will be n square now, and plus 2 times cosine nx divided by n power 3, limit is 0 to pi. Okay, so now if we substitute x equals to 0, this x term will be 0, and this term will remain. And on the other hand, when we substitute pi, the sine term will be 0. Cosine n pi will be minus 1 power n. So what shall we get is, for x equals to pi, we get pi square minus 1 power n. So that is minus 1 power n plus 1 divided by n, right? Because cosine n pi is minus 1 power n. For pi, we have this term remaining, so that is plus 2 minus 1 power n divided by n power 3, and the x equals to 0, we have only this term, right? The last term with the negative sign. So that means minus 2 divided by n cube. Cosine 0 is 1. So we get this now, right? Just check that if there is any mistake. Okay, so
Correct.
right, so this is what we are getting, and this last term involves essentially 2 power n power 3 terms minus 1 power n minus 1, right? So we can take 2 divided by n power 3 common. So this term depends on whether n is odd or even. So depending on that, this term will be either 0 or 0 or minus 2, right? So let us assume that two cases. The first case is if n is equals to even number, then if you substitute n is equals to 2k, then this will be 1, right? Minus 1 power 2k will be 1. So the last term will vanish and first term will become, yeah, so pi times pi square will cancel 1 pi, and we get minus pi divided by 2k. Similarly, if it is an odd number, so let us say it is 2k minus 1, we are writing k 1 2 up to infinity. So if k is 1, then we start with 1, then for k is equals to 1 we get 2 here, then for k is equals to 2 3 will come, k is equals to 4, k is equals to 2 we get 4 here. So that way we can cover all values of n, and for n is equals to 2k minus 1, this term will be minus 2 times 2 divided by n power 3, where n is 2k minus 1. So essentially we get pi divided by 2k minus 1 minus 4 divided by n cube. Alright, so depending on whether n is odd or n is even, we have got this formula. So now let us substitute all these things what we found. So what is this term? We found basically bn, depending on whether n is odd or n is even. So let us write down the Fourier series now. So Fourier series of the given function fx is 1 by 2 a0. A0 is pi square by 3. So 1 by 2 pi square by 3 is pi square by 6 plus summation 1 to infinity an. So what is an? An is this number, right? So let us substitute that 2 minus 1 power n divided by n square cosine nx, right? An cosine x plus we have summation bn sin nx, and bn sin nx we have divided into two parts, right? Where k is a natural number, so that means we get two series. The first series is k is 1 to infinity b to k sine 2k pi kx plus k1 to infinity 2k minus 1 x, right? So these two parts essentially forms cover all the terms bn, b1, b2, b3 up to bn, so on. So now let us substitute this term. So basically this is b2k and this term is b2k minus 1. So essentially if we substitute these terms, we shall get pi square by 6 plus an part plus a is equals to 1 to infinity. Yeah, so b2k term is minus pi by 2k sine 2k pi, right? And the last term is the odd bk, that is pi divided by 2k minus 1 4 divided by 2k minus 1 power 3 sine 2k minus 1 x. So we found the Fourier series expansion. Now we know that the given function satisfies all the properties of the theorem. So what is the property of the theorem? The function should have left and right derivative, and it should be continuous and periodic. So this function satisfies all the properties. So that means the Fourier series converges. So this function is continuous at 0, right? This function is continuous at 0. So that means at f0 we get the value of the series at 0. So substitute x equals to 0, we get, so the value of the function at 0, what is that? At x equals to 0, value of the function is x square, and x is 0, that means the value of the function is 0. So fx is 0. Now we shall find the right side at x equals to 0. So we get 0 is equals to right side. So right side we know that we substitute, yes, we forgot to write x here, right? It should be sine nx, n pi x. Pi is not there, right? Or pi is there?
No, sir, pi is not there.
Pi is not there, right? Okay, so let me just check once again. We have written yeah, so that is not there. So now when we substitute x equals to 0, then clearly this sign terms will be 0 when x equals to 0. Cos 0 is 1. So we get pi square by 6. Cos 0 is 1. That means only we get this part. Correct? So this is n square. So what we get is 0 is equals to, just a minute, we get 0 is equals to pi square by 6 plus summation 2 power minus 1 power n divided by n square 0 to infinity. So what did we get? We get the expansion of this function in terms of pi square by 6. So let us just write down what we got is, we got, if we take the series term on the other side, we get summation 1 to infinity 2 minus 1 power n plus 1 divided by n square is equals to pi square by 6, right? Because we are taking this term on the other side, so it will become negative. So that will give us minus 1 power n plus 1, and then this 2 is common, so we can divide on the other side. So essentially we get the series and 1 to infinity pi square by 12. So this is what is this series? This series is basically 1 minus 2 square plus 3 square 4 square pi square by 12, right? So uh, we were looking for pi square by 6, but first we have taken the simplest case for x equals to 0. Now the second case is you substitute x equals to pi, right? So check for x equals to pi. In this case we will get the expansion of pi square by 6. So substitute x equals to pi in the Fourier series. Okay, so I think this is enough for today. Let me stop here.